It's a pleasure to be here with you all. Today I'm going to be talking about scene reconstruction from cameras and how we can use differentiable rendering to improve our quality of scene reconstruction. Okay? So this does relate a lot to what Faye was talking about yesterday. And every camera now is basically a multi-camera system. Okay? We no longer have single cameras when we capture an image. We often have multiple information available to us. Okay? And so one of the core topics that we study is how we can build scene reconstruction tools for multi-camera systems, and then how we can use those reconstructions for editing, for computer graphics applications, and things like this. Differentiable rendering is a new technique that allows us to improve the quality of our reconstructions. So let's take a step back. When we talk about computer graphics, we typically talk about forward rendering. I have a model, and I have some algorithm that turns that model into a simulation of flight. So, and we've been doing this for about 60 years, and throughout that time, we've built all different kinds of representations and methods that span a space of different constraints at the application level, at the task level, how fast it needs to be, how much quality it needs. Okay? And the space is very complicated. Right? It requires an expert, the people in this room, to be able to navigate all of this complexity of choice and representation. Right? And in some sense, that's what makes our field interesting. If there was just one way to do everything, it would be very simple. Okay? So, then we come to differentiable rendering. Right? It's a new set of tools, new formulations, new hardware that makes it possible. Right? We have these amazing new results, some of which hit archive every day, and it's so much hard to keep track of. And we even have these neural rendering methods, right? Like NERF, might have heard of, or neural seed flow fields. Okay, and there's this excitement, this momentum. It feels like maybe many problems are solvable, maybe any problem is solvable, right? But let's temper our expectations a little bit. All of the complexity that we had in forward rendering, we now equivalently have in differential rendering, except now we have a horrible optimization problem on top of all of that complexity. Right? So, well, let's see how well we can do. Just to give us a recap of what we really mean by differentiable rendering, well, I have some initialization of my scene via its parameters. In this case, the Utah teapot is wanting to match a target image. Okay? And through typically a gradient descent process, in this case, I'm optimizing the camera pose via, this is a differential rasterizer. Okay? And I'm going to determine some pixel-wise loss that allows me to backpropagate derivatives through my rendering system back to the parameters of the scene model. And I have some function R, which I'm going to treat as a renderer. Right? But I'm tricky. You have to have the right representation to get the right result. Here we're optimizing the vertex positions of the teapot to match the square from a single view. And the answer is correct when it's projected from one particular viewpoint. Right? But it doesn't have the constraints to solve this problem any better from other views. Right? And so the representation and the way that we solve the problem has to fit the task. Okay. When we talk about scene reconstruction, integrating all this information from multiple cameras, we have a spectrum of approaches that we can use. Typically, we think of wide baseline cases where the cameras are very far apart. You might think of like a light stage or a big camera rig. Right? And this is a hard problem. It requires me to have explicit geometry, typically surfaces, meshes, to be able to cover this wide baseline. all the way down to narrow baseline cases like these very small baselines on smartphones, where I can use simpler geometry, maybe image-based rendering techniques, to be able to cover the difference. And of course, the gap between these two, you can think conceptually of moving your smartphone around. Right? If I make it portable, then I can generate these white baselines. Similarly, when we talk about rendering, there's this spectrum of different approaches. Path tracing, which is very expensive, but high quality. Rasterization, which we use for real-time graphics. Okay, image-based rendering, when we talk about photographic media, and even strange, curious things like point-based rendering, which exist in there too, right? All of these tools are available to us. Finally, one more spectrum I'm going to introduce, and this is the way that we solve the problem. So you could try to implement an exact differentiable renderer, or I might try and take a neural network approximation approach, what I'm going to call a neural field approach. Or I could even do something like use some image-to-image based rendering using computational neural networks, or a UNet, like an auto-encoding system. Okay, and they each, again, have all of these different complex trade-offs that are useful for different applications. All right, so that's the scene we've set. So I'm going to talk about 3 projects today that are going to hit different points on each of these 3 spectra. Okay, first is a piece of work that tries to generate VR video for cameras that are arranged in a sphere. This is going to use very fast image-to-image based techniques and a differential renderer. And I'll talk briefly about a technique for reconstructing scenes using narrower baseline cameras. And this is a point-based rendering method. Okay? And it takes a few minutes to compute, not real time. Okay? And then I'm going to talk about some very recent work that is high quality, but very slow, and it uses neural volumetric renderer to give you back very detailed scene reconstructions just from a smartphone. Okay. Ready to go? All right. So let's go to the first project. It's called matryodshka, and this was presented at ECCD last year. And this is a collaboration between Dr. Brown and my colleague Mr. Richard at University of Bath. Okay, when we talk about virtual reality, typically we think of computer graphics and rendering. And when we're solely in the digital world, it's very easy to reproduce 3 key visual effects to give a sense of realism. Right? These are the fact that I can rotate my head in any direction and look around. The fact that I see different images with both eyes, this is binocular stereo. And the fact that I can translate my head as well. In fact, every time you rotate your head, it's also a translation because you have a neck. So how can I recreate what we call 6-DoF or 6 degree of freedom, 6-DoF effects for camera captured beyond video? This is the question. So a quick recap on some 360 degree imaging basics. Great. Sorry about the little pop-up. Okay. So here's a typical monocular 360 degree video. Right? This one, in fact, is rendered with computer graphics. Okay. And how this is stored in memory is through an epirectangular projection. This is a map projection, as might be seen when you unwrap a globe. Okay? And theta here is the latitude of the globe, and P here is the longitude of the globe. All right. So when I have monocular 360-degree imaging, I do not perceive the binocular stereo effects or the motion parallax effects. It looks okay, right? And it looks, oh, it's submersive, right? It doesn't really feel like you're there. It looks like you're looking at a very big panorama. Yeah. Here's a visual demonstration of what that looks like from when you're inside the sphere. So this is me in a VR headset. I don't have motion parallax. So when you look at the chair, when I translate my head, it doesn't move relative to the back wall. Yeah? This means that it doesn't feel like a real place. Visually, it doesn't feel like a real place. If you look at the thermostat there, it doesn't occlude when I change my head. Okay, so can we fix it? You may have seen or heard of, there you go, stereo 360 imagery. It sounds like it should exist. It's how when you have two cameras next to each other. But it's not quite how it works. The ray space that this camera captures can be used to try to synthesize two views, a left eye and a right eye, while solving the occlusion problems. Has anybody ever looked at any stereo 360 imagery? Okay, it looks super weird. Super weird. It's very odd. The disparity looks wrong, and when I look at it, I get quite sick. It's very fast. It's quite difficult to have correct binocular effects, or it's approximately correct, but not motion parallax. It looks very, 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 very odd. I think it looks worse than the monocular stuff. Okay, so that's no good. So, what do we need to do? Well, I said that we had stereo, right? And so maybe we can do some kind of reconstruction. Right? So we're going to try and do some kind of reconstruction. Suppose I had depth. Suppose I had depth along each ray. Then I could re-render the scene in different fashions. One way I can do that is by meshing the depth, okay, and then re-rendering the depth based on some new virtual camera. This is a very common approach, right? Sometimes people even go further and do layer-based decompositions of the mesh. Okay. One of the problems is that it's very hard to represent things behind other things. Motion parallax means I will disocclude content in the scene, and I need to have some kind of scene representation that allows me to represent occlusions. Okay. What you see on the image here on the left, this is what it looks like when I disocclude content with this mesh-based depth method. Okay. What happens is that I get stretching and the triangles get stretched over the screen. It doesn't look particularly good. So instead, the two reasons we're going to introduce a different approach, and this is based on multi-planar images, which go all the way back to Disney. So in animated films, oftentimes there's motion parallax. You'll see the background moving slower than the characters in the foreground as they walk through the forest. Okay, how was that accomplished? Well, the camera system was mounted on a rail with this rack of plates, transparent plates, and the artists would paint on the plates. Okay? And then the little wheels here were geared such that they moved at different speeds depending on how far away they were from the camera. And this induces the effect of motion parallax in the camera. Digitally, how do I do that? Well, I need a bunch of images, and each of them needs RGB and alpha. Okay, and then I'm going to overcomposite these to be able to produce the final effect. All right, so now we're in the 360 domain. Now we need multi-sphere images. Okay. And the little graphic here, these are our normal viewpoints for as I move my head around. Okay. And it looks a bit like shells within shells within shells. It looks a bit like Russian dolls, which is why this project is called Reconstruction. So how do I render this? Well, this is my series of concentric spheres. And I'm going to shoot a ray through them, and I'm going to query the alpha and the color at each stage. And then I have a very simple product that accumulates this transparency as I go through the space. And then I multiply this by the color that is stored at each position. And then that is the final color that gets written out to the camera, to the virtual camera. And I render one of those for each eye. And this allows me to reproduce the motion parallax and financial stereo effects. And it allows me to handle occluded content because I can put stuff behind other things at different layers of the sequence. This is also differentiable, which is nice. It's the products. It's as a representation, it's just a bunch of images, right? Which means that I can put it into convolutional neural network approaches, and it can be very fast. Okay, and so here's what it looks like. I'm going to, if you recall it, what we had before, we had no motion parallax on the chair, right? And here on the right-hand side now is the representation through the multi-spheres, and I get motion parallax. Okay. But it's very hard to explain the difference without being in the headset. It looks very subtle, but it is like night and day. So when I'm in this one, I can last about 10 minutes before I start to get sick. Okay? And this I can use for like an hour. Okay? I have tricked the brain such that my visual system now matches my vestibular system, which tells me where my head is. And I managed to fix the problems. So this feels very comfortable. Okay, let's look at the architecture of how this is pulled off. It's actually reasonably simple. There's a couple of tricks. So my input is this format called omnidirectional stereo, which is a left 360 image and a right 360 image for the two eyes. It's a bit weird, but let's go with it. And then this usually comes off the camera at 4K by 4K, something like that. So very high resolution. So we downsample it because we just can't handle too much resolution right now. And then we perform a standard stereo reconstruction step, which is called a plane sweep volume reconstruction, or in our case, a sphere sweep volume reconstruction. This is like saying, suppose the depths were 3 meters. If I reproject both images to a sphere at that point, how much do they overlap? I compute the correlation. And I do that for a set of different depths. And then I store that as a block of memory, one on the left, one on the right hand. Okay, and then that goes into a UNet, whose job is to output the multi-sphere image representation. And we said that this was formed of a set of raster images that have both color and alpha. Okay. And this is a depiction of them here. You can see that stuff that is close to the front of the scene exists in some of the earlier layers. And then as I go further back, I see more and more content. And some of that is the discrete content. But the little trick that you do, which is a bit different from how other people do this, you don't actually predict directly with color. Many methods just predict with color, but we don't do that. Instead, we predict blending weights between the left eye and the right eye. Okay. This has two benefits. It lets you use all of the rays. So if only the left eye sees something, then I say all of my weight should be in the left eye. And the second thing is that I can upsample these blending weights back to 4K by 4K, and then use the original high resolution video with this like lower resolution pseudo depth that comes from the alphas and the representation. So it's increased volume. Okay, we're going to do this very fast. We can do this about a frame rate. Okay, modern graphics cards are amazing. Quickly. Which means that we can take a feed of the video, or we can take a pre-captured video, and then turn it into fixed off video. Very, very good. But now I have a problem, because now I'm doing video. And in your heads, as soon as you think video, you think temporal consistency. Okay, so let's add some temporal consistency. Well, this is typically how you do it, but I'm going to take the sphere sweep volume of the MSI from frame 1, and then I'm going to take the same thing from frame 2, and then I'm going to compute optical flow between them, and then I'm somehow going to refine the MSIs based on the flow. I'm going to project one, the other, right? Everybody's seen this, right? Okay, this is really expensive because now I have to compute optical flow between every pair of frames. The optical flow itself will be in error, right? So I'm going to introduce error, and then I'm also going to introduce a temporal dependence, which introduces latency, right? Which is also bound to the optical. So let's not do that. Let's do something else. This is a very simple trick that you can use almost everywhere. This should say at the top, single frame transform regularization. This is a kind of self-supervision, which is a total hack, but it works really well. Okay, so here we go. So I take my original correlation volume, this sphere sweep volume, and I infer an MSI, a multi-slit image, using my unit. And then I transform the spheres at which I first estimated the correlation volume. And then I infer a second MSI. This is the training time. It's just a little bit different in space from the first one. And I say that difference should be about the difference between one video frame and the next video frame. Okay. And then I say, well, if I render some target camera that is about in that position, I should get about the same output. Right? This is saying if the depth were correct, and I did do this transformation, I should get the same result approximately in my output. So then I'm just going to penalize a loss, say that these two things should be about the same. Okay? So hack. It shouldn't really work. Not particularly principled. But what we're trying to do is minimize this like random flicker that gets introduced whenever you do video processing. Right? Okay, so let's see if it works. Okay, so at the top is the version that hasn't had this single frame transform regularization. Okay, and you can see this is edge on the bar. This is a cafeteria scene up here. Right? It flickers really bad. Right? Similarly, there's like phantom geometry here. It's in front of the benches. Right? Also bad. Do this regularization trick. Doesn't really affect image quality, but it gets rid of the flicker and it improves the depth. It's like win-win, but no cost. It's just a training time cost. Okay, so here's the cafeteria scene that you just saw. And this is a static camera. So all of this is virtual camera motion that's induced through the model. You can see some bits where it has cheap. So this bar here is a disoccluded region. The camera never moved. So what did it do? Well, it learned to put some floor behind the bar at the front. Here's a comparison to the approach that we said at the beginning, where we take the depth map and we mesh it, and then we draw it. Okay? And you can see that this bar region, what I'm left with is the smudging of the color at one side of that mesh, occlusion edge, and the color of the other, right? And in our case, the interface approach has managed to do something more positive. Okay, not everything is rosy in Joshka land. So if you want to do this fast enough, you can only use about 32 layers within your shell-based representation, which limits the precision of the depth of the scenes that you can represent. And because we're at this low spatial resolution, then we can't really do the thin structures very well. Okay, so there's all of these trade-offs that are inbuilt into this approach. But actually, it kind of works, which is a bit surprising. Right? And I can do this very fast. The quality is okay. It's not amazing, but it's okay. And it's useful for things like telecommunication or robotic teleoperation, perhaps, where I must do things in real time. Okay, any questions?
Yeah, maybe what about the training? How do you train the different data sets?
Yeah, I completely missed that. We have a synthetic data set of real captured scenes that we then render using stereo 360 virtual camera. Yeah, and that's all public. If anybody else wants to load that, the data and the renderer. Yeah, and then it's just trained with a 2+ loss using the differential renderer that's built. Yeah. Okay. All right, so we had fixed depths, and then we had RGBA, and the optimization problem that we were solving was to predict the color and the opacity, actually, the blending weights and the opacity in each of these layers. Right? We could do that very, very quickly. Now we're going to move to a more complicated optimization problem that is based around being able now to optimize the depths specifically. Okay, previously the depths were fixed, but now we're saying I'm going to optimize the depths. And the setting for this one is these narrow baseline cameras, like light field cameras or multi-sensor cameras. And this is work from my PhD student, Numan Khan, who graduated on Thursday, so congratulations to him. And my colleague, Ben Kim, in South Korea at the Korea Advanced Institute of Science and Technology called PLACE. So this is what's called differentiable diffusion for dense depth estimation. Right? And it's related to what Bea was talking about yesterday with her variational framework for depth estimation too. Right? The graphic here says, imagine I had sparse depth points, and I used a variational method, a diffusion-based approach, to fill in the gaps. Right? Typically, what I end up with is something that looks like this, the naive diffusion version. It's kind of fuzzy, right? It's quite hard to know where the edges are, and it's quite hard to get them right. And this is an approach to fix those problems using differentiable rendering. So, some background. We're doing depth estimation. What are the core problems in depth estimation that exist in all methods? Okay. Well, what do you do in regions where you have no texture? I'm imaging the scene from multiple cameras, and I'm saying that the texture information in the scene is going to provide me with an estimate of the correlation. That gives me disparity, and then I can turn that back into depth. But in regions with no texture, I don't know what to do. There's no correlation that I can do. typically leaves me with only sparse samples of where the depth is in the scene. So I need to turn this into a dense depth map for many applications. One application that you might think of is if I'm combining like a LiDAR system with an RGB system for autonomous driving, for instance. I have sparse depth samples, but oftentimes I really need some more spatial resolution. Right, that one depth sample point that I saw for the pedestrian probably isn't enough, and maybe I can use my RGB sensor to improve things. Right? It's called densification. Okay. And lots of methods use deep learning to try to predict what the dense estimate should be. Right? We used to do this with diffusion-based methods. Right? We used to. Right? And the intuition is good. It's saying, for some scene, right, just estimate depth where you know you can, where I know I have these strong textures, like the edges, and then fill in the rest using some smoothness assumption. Right? And for many scenes, this is a good assumption. Right? That the difference between the edges is smooth in depth. Okay. This can be really accurate as long as the sparse points are also themselves accurate and also noise-free. Okay. So here's the depth for the scene computed when I have correct positions and correct weights for the smoothing process. Looks good. But, oh wait. There you go. And this is conceptually the same as in 2D images, where we say, well, what is an image? Well, it's a bunch of edges with a smooth function in between. Right? And that's all there is. All I have is some density gradients. Okay? It's literally what an image is. Okay, but as soon as I have error in the points, my result starts to look bad. As soon as I have the wrong weights in my model, it starts to look bad. And so the problem is not the diffusion. Right? It's not the smoothness assumption that's the problem. The problem is I have the wrong point positions, I have the wrong point depths, I have the wrong weights associated with those points. Right, so nobody uses the same. Everybody just does the other. Okay. Okay, that's it. We're done. That's the end of studying this topic. We can all go home. All right. So we're not going to do that. We're going to do something else. Here's what it looks like right now, right? Shi et al. And Li et al. Are both deep learning-based methods, and our diffusion-based methods right now kind of doesn't stand up. So you're asking yourself, James, what if we could denoise the sparse points? Yeah, that sounds like a good idea. Okay, and we're going to use differential render, but it's going to be kind of complicated. We need a differential representation of sparse points. Okay. We need somehow a differential diffusion process. Actually, that was not too bad. And then I'm going to need a differentiable image-based point renderer to hook this all together and minimize the loss between the RGB images and the depth. Okay, but there's no neural anything, right? There's no prediction, there's no CNN, right? It's just differentiable render. Okay, so here's the high-level diagram. I take in multi-view images from my camera system, and I compute sparse depth points where I know I have high confidence. Okay? And there's all kinds of different methods you can do this with. And then I have my differentiable point-based rendering algorithm. And then I have my differentiable diffusion solver that turns this from a sparse set of points into a dense depth map. And then I'm going to take that depth map and use an image-based warping method to re-render the scene based on that depth back into the input camera views. And then for each of those, I'm going to compute the loss that's going to optimize the point constraints to denoise the points. Okay? There's a lot of subtlety in getting this to work, but at a high level, what I need to be able to do is differentiate the points in the spatial domain, in X and Y, and in Z. I'm going to model them as little Gaussians that get splattered to the screen. And the depth value itself, I'm going to model using radiative transport. So I'm going to say that each of these has some transmission, just like in the model that we saw in matryodshka. It has some alpha, right? And I'm going to composite them and accumulate that transmission to work out the value. So, let's get this. The equation looks very similar. It's a product, but now I have a term for Z that allows me to move this thing in depth, whereas before I was just at fixed depths. Okay. This is what it looks like when it goes on the screen. It's the scene, right? It looks kind of blobby. I need these gases to be quite big because I need to be able to differentiate their position in X and Y. But it's okay because I have a data term that I can also simultaneously optimize that reduces these down to sharp points. Here's the initial depth from that scene. It has a ton of errors. Right? I have some points that are completely in the wrong Z, at the wrong depth. Right? And through this process, I can get it into something that looks like that on the right. And this is better than the deep learning based methods. Okay, I'll say that. All right, where does this fail? Well, anytime I have a non-Lambert surface, anytime there's specular reflection, view-dependent effect, I'm still only modeling depth. And so I can't handle this well. So here's the ground truth. Sorry, it's cut off. This is the ground truth depth for this scene. This is a static scene. And here is our estimate. And our estimate looks pretty good, apart from the materials that are shiny or glossy, like the television here has this strong specular reflection, or the piano here doesn't quite come out right. But otherwise, it works okay. It works okay. Right, how many? In your head, you're going, wow, this is an optimization embedded within an optimization. This must be really expensive. And actually, no, it's not. So you can implement this with tile-based renderer. Generally, only small regions affect each other, as long as your points are sufficiently dense. And that's not too bad for most of these narrow baseline camera systems. You can do that. And so you can solve this optimization in the order of minutes. Right? It's not real time, but you can solve this in the order of minutes for a scene. Yeah. Okay. So on to our last project. So we've gone from real time to minutes, and now we're going to go to hours, right? But we're going to increase the flexibility of our representation. Right? We've added complexity in each case, and here we're going to build on this now famous neural radiance fields work. And so we're going to introduce neural network approximations now to rendering functions. This is called it's time of flight plus nerve. So it's torf plus nerve, so it's turf. Okay? Yeah, that was a bit fun. And it's in the slide. Right. So the goal here is what we had before, scene reconstruction. But now we're going to do dynamic scenes. And it's going to be like sort of monocular. It's going to be RGB plus time of flight. So I just have one color view, but then I get a pretty good depth signal already. And my job is to reconstruct a time varying scene representation. what is a time of flight camera? Well, it's this thing on the back of your iPhone. Okay. This is now going to become everywhere. Right? Time of flight provides us with the ability to do augmented reality very well by providing us with these depth cues. But actually, the signal is not that good. Here are some sequences that we shot with a research time of flight camera, and this is already much better than the depth that you can get off the back of an iPhone. This is 640 by 640, the iPhone is like 200 by 200 or something. Looks pretty good, but there's many problems. You can see these high errors on areas where the object itself doesn't reflect a lot of light. You can see these complicated, noisy areas, or here. This one's not reflected, right? But this area here is very noisy, it doesn't look very good. And this is because of what's called multipath interference. So the light is bouncing in many different ways, and the sensor can't resolve what the depth is. And then in this one, we have some weird thing going on at the back here, where the scene looks like it's really close, even though it's very far away. Wait. That's a good question, and I'm going to try and answer that in a very short amount of time. Sorry. But I'm very happy to talk about this in detail later on. The method that we propose is able to turn those depths into something that looks like this. Okay? And these are actually novel views rendered from different camera positions that were actually captured at the time from this space-time body. When we talk about, I'm going to skip over some stuff in the interest of time. So you'll have to forgive me for the bits that don't make sense on the slides. When we talk about time of flight cameras, one of the core techniques that's used is called a continuous wave time of flight. Typically, you think of time of flight as like a pulse of light coming out and then counting how long it takes to come back. Right? That's one method, but it's used for like architectural survey and things like that. There's another method which is called continuous wave time of flight, where a light source modulates its output amount of light amplitude in a sinusoidal way. And then we look at the sensor to see the correlation between the outgoing sinusoid and the incoming sinusoid, how the intensity of the light varies as it comes in. And we can compute the depth of the scene by the phase offset between the light that went out and the light that went in. Phase offset is proportional to the depth of the scene. Okay, this is the core concept. Now, because this is a repeating signal, we call these phasor images. The images that get captured by the sensor measure the phase difference and also the amplitude difference of the outgoing wave. So this is called a phasor image. Okay, I appreciate this is perhaps a little. So the method defines a rendering function, the time of flight cameras based on this concept, and then integrates this into the NERV framework. I'm going to show you the problems with phasor imaging and how we can fix them. We saw there's three different kinds of errors, right? The low noise, the multipath interference, and then this distance that was off in the background, right? But it was actually close. Okay, so in low noise regions, why does working in this phasor space help? So here's our phasor, amplitude, this is the phase. And you can think of it as a vector in complex space that has a length and an angle. Okay. And my scene, there's the amplitude in the phase. My scene, as it gets brighter and darker, we're going to see the change that's induced on the vectors. Okay. Sorry, as it gets closer at that part. Okay. So, oops. So the phase difference relates to the depth, and the amplitude relates to the brightness of the light that is returned at that particular point. So when there's low reflectance, this vector is small. Okay. When there's multiple reflections, we're going to introduce some blast here. What I end up with is a superposition of phases, which accommodates this multipath interference. And the last one is to do with this depth that was completely wrong. Actually, this is called phase wrapping. It happens when your correlation can't know whether you're in one wavelength or the next wavelength. So there's some distance beyond which everything looks like it's really close to it. Okay. All right, so how do we fix this in 2 minutes? When we solve from here, builds this volume. Okay. We simultaneously reconstruct the RGB images and the phasor images from the time of flight camera using the same volume of stuff. So nerve says within the volume, where is their surfaces? Where is their density actually? Okay. And for the color cameras, do stereo reconstruction. And for the time of flight cameras, do their phasor-based image reconstruction. The stuff in the scene has to be in the same place for these to match up. This is sufficient. Oh, and then we penalize altitude loss. This is sufficient to resolve all of those problems. Doesn't sound like it is. Like how could it be? But the idea is that when the RGB is correct, but the top is wrong, it's okay. Or when the top is right, but the RGB is wrong, it's okay. I'm trading the benefits of both of these. So the key one is the phase wrapping. We said that this part of the scene that was very far away is caused by the fact that the correlation is picking the wrong phase. But when you look at the RGB camera, there's only one phase offset that would match the correct answer. And so this reconstructs the correct volume and just automatically resolves the phase range. All right. I'm going to show you a slide. You can see the comparison between the kind of quality you can get from a time of flight plus RGB system and this optimization versus other attempts to use more classic depth reconstruction methods. So video nerve is a classic stereo-based depth reconstruction method with some heavy regularization, and the detail is just completely different. Right? And NSFF uses a monocular learning-based like CNN to do depth estimation and then feed that into the RGB system. And it is also like of a different quality than what you can get from a time of flight camera. All right. So I wrap up. We saw 3 different representations for differential rendering. We saw very, very fast but not particularly flexible rendering system for LIRIS. I was using prediction, using a CNN to learn how to predict these multi-sphere images. We saw this splatting-based plus diffusion approach for doing pure differentiable rendering, no prediction, no learning. And then we saw this third model, which is a neural renderer for doing volume-based rendering, again, no prediction. And each of them has different characteristics and a few times and the different qualities out there. All right, I will stop there. Thank you very much for your lengthy attention. And does anybody have a question?
Just a question for your last project. So you are actually optimizing the depth values or the phase of amplitude that allows to reconstruct the depth values?
We optimize the phase and amplitude. The objective is only computed on the phase and amplitude.
So how do you get the phase of amplitude for like standard? Is it a data that you easily get, or I assume that usually they would just give you the depth value.
That's right. So you can't do this right now off a regular iPhone. You don't have API access to what's called like the raw samples from the sensor. You need access to the raw samples from the sensor to be able to do this. But Apple could certainly do this. Right. So as an API, you only get the return depths.
Okay, so in practice, you use another device.
That's right. But we have a camera that provides us with the raw sensor measurements. Then from that, we don't compute depths. We instead stay in this phase of space and just optimize the phase of space.
Okay.
Yeah.
Good question for your last project.
Right.
The computation time, training time is not person as for.
That's right.
So that's several hours for.
Yep, sure is.
Okay.
So NERF takes, I don't know, 12 hours to converge on most, approximately. Like the quality improves as you leave it running for longer. This is actually a more complicated problem because you're integrating video basically. And so I think we run each of these for about a day. Yeah. There is a trend, should we say, of recent works that show that you can do this much faster. And you should be able to do a much better job by the fact that most of the scene is already at the correct depth from the camera itself. It's just these outliers that are a real pain. So I wouldn't be surprised if in a couple of years' time we have this down to something that's useful. Now, right now it's not useful, it's just a demonstration that solving this optimization in this way can fix a lot of the problems with time of flight direct depth. Anybody else before they?
Still again on the last project, very two questions. The first one is how can you capture some conflicts or reflections or things like that where the image doesn't match with the phase images.
Right.
And second, what is the impact on the reconstructed RGB image? Are there information you can use from that reconstructed?
Okay, so for caustics, what you end up reconstructing is this superposition phaser. Right? So I don't ever reconstruct anything like a material, right? And I don't really reconstruct correct light paths. All I say is that whatever the volume representation has been optimized to, it must reproduce this superposition effect. I have a slide. This is the most complex scene that we demonstrate, and we do glass pretty well. I don't guarantee that that's at the right depth. right? I only guarantee that the output phases are correct, right? And that's a very different guarantee. It fixes a lot of the visual artifacts when you're doing novel view rendering. Like all of these images in the second and third column, they're all novel views. But it's not a guarantee that you actually know what's going on in the scene. And then the second question was,
on the reconstructed RGB image, is there some information that you can use? You only show the phase images.
Oh, that's right. So it's implicit in the optimization. And so all of that information is always being used to whatever extent is required to solve the objective. Beyond that, I don't really know how to answer the question because the setup is incredibly simple. Once you've expressed it in these terms, the RGB information is definitely being used. It is the thing that helps you resolve the phase wrapping, especially. Maybe there's more to your question, and maybe we should come back afterwards to.
Yeah. So basically, if you look at the reconstructed RGB on this very specific caustic kind of reflection effects, I would expect that in the RGB image, which is very tiny for sure, you have probably washed out all the reflections or remove the caustics, or I would expect some stuff like that.
But it doesn't happen. No. It definitely happens in nerve. So reproducing high frequency reflections in nerve is very hard. So it definitely happens in nerve. So I don't have a good answer, and maybe that's something we should look at more.
For your second project, how far is it from the video-based rendering? Is it just a matter of computational time, or
how far is it from
video-based rendering?
Video.
For video.
It takes like 10 minutes to frame.
But yeah, that's it. Apart from that, that would work out of the box.
Yep. Yeah, but 10 minutes to frame is just too long.
Yeah.
It's still in yours.
I mean, that's true. If you had one thing that really helps in the last project is that actually we solved two separate optimization problems. We solved an optimization problem for the static part of the scene, and then we solved one for the dynamic part of the scene separately. And that gives you a way to minimize the complexity of the optimization problem because most of the scene is static. And maybe you could do the same thing for the second one if you had a set of points that you knew were static. It would be much faster.
I have you.
Yes, sorry. Question about the source project. You know, what kind of light source?
It's just an infrared light. Sometimes people use laser light. Sometimes people use non-collimated light. But it's just infrared, and that means that it doesn't intersect the visible part of the spectrum.
If I want, but the class blocks the URL, or
it depends on the glass.
Okay.
You could definitely have glass that is infrared. I think glass often is UV restricted, so that you don't get sunburn indoors.
I actually have a quite general question. At the beginning, you mentioned the Planoxel's work.
Oh yeah.
That's quite recent papers. I haven't read it yet, but
it's going to come out 2 years ago.
but it looks like they managed to get results that are almost as good as nerve, but much faster. With only like optimizing your representation with voxels without neural networks.
That's right.
And so I was wondering if you had any intuition about what are the advantages of using neural network as a way to represent the scene. Because it looks like in this paper they basically show that the contribution is more about using differentiable volume rendering as a loss instead of using the network as a representation.
It's a great question. And one of the reasons why it's important to think about all of the things you could do, right, is that maybe you don't need to do these things. Right? So the middle project is exactly the same style as the Tonoxal's paper. Right? And so equivalently, there's a version of turf that uses Tonoxals. Right? So what's the benefit of using like a multi-layer perceptron doing function approximation? So my hunch is when your optimization problem is hard, whatever that means, right? The MLP is more likely to do well. Right? Like it's very hard often to define the right problem such that your straightforward differential rhetoric actually converges to a solution. So one of the benefits, one of the things that makes it possible, the middle project, is that the initialization is already quite good. Like we're already reasonably close to the right result. And that's because we're basically using like classic computer vision methods to get us 95% of the way there. Right? So the optimization is already well initialized. And if you just start off the middle renderer with a constant depth everywhere, it won't converge. So the thing I don't yet understand is why Tonoxals works from an arbitrary initialization. And I think that the benefit of the MLP is often that it lets you solve a more complicated or less well-posed optimization problem. You can think of it a bit like there's all kinds of ways to interpret what MLP does, but because it's this random initialization with parts of the function all over the place, right? It's a bit like a multi-star optimization problem. And there's people have studied through this, they generally converge to a good optimum because of this randomness at the edge. So yeah, it's a great question.
I have a question, and it's really a question from someone far. And Bruno is asking, thanking you for the talk. And he was wondering how expensive and how big heavy the multicam and torf sensors are compared to older structured line infrared technologies such as RealSense. And the underlying question is, can it be easily embedded in a robot or a drone?
Oh, in terms of money, that was the expense, right? I really have no idea. I'm pretty sure Apple is charging you $1,000 for the iPhone because of sensor is so expensive. Sony have one in their cell phone. Many Samsung have one, right? So I don't think expense is going to be a barrier going forward. It's more like the novelty of it, right? And then the second question was, could you embed it in a robot? Yes, if you can get it to work fast enough. Right? Robots have to be real time. And simply speaking, whenever you look at robot demos, right, you have to be really careful. It looks amazing, and then you have to look at the bottom right-hand corner, because then there's like a sped up 10x. Always. Any robot video you look at. And so if we can do like sped up 1000x in the corner, then maybe you can do yeah, so it's a question of speed.
How much better is the real-time sensors from RealSense are? Well, not so good in terms of quality of it.
They have different characteristics. Yeah. They're fine. So one of the benefits of structured light approaches like the RealSense cameras is that they're better with motion. In principle, you can make them work faster because they're single shot. The way that the continuous wave time of flight cameras work is that they actually integrate information over multiple frames. And that means that they are inherently not well positioned to handle dynamic things. You have to do additional processing steps to accommodate. So that's one benefit. but then they're less accurate. The depth estimate that comes out is less accurate.
Did you try with a large motion for the kind of lights? Because we see
Yeah.
the same kind of artifacts as the ERS was showing yesterday.
Yeah. So I think this is the kind of artifact you would see in a large motion. Yeah. All right, I have one last thing as a concluding remark. If you're interested in neural representations, you just put a survey paper out. It's called Neural Fields in Visual Computing and Beyond. It's on the archive right now. There's a website that goes with it. There's this thing on the right-hand side. And so you can search for all of the neural field papers that exist right now in visual computing. And we made a little promo. Yeah, it's pretty cool. You can go and filter by all kinds of things. You can push one button and get the bit tech for the paper. 260. Yeah, it's nice. All right. Thank you all very much for the great questions and your attention today.
Thank you.